Thank you. Okay, so I'm going to explain in that talk what is wave, essentially, the great lines at least, and how we can select parameters for having a secure scheme in the sense that the computational assumptions are true. So wave is an Hash-unsigned digital signature scheme based on codes. It uses the so-called generalized UU plus V ternary codes, which feature a decoding algorithm which is slightly more efficient than the decoding algorithm of random code. So we use this advantage to produce a signature by being able to decode a bit more efficiently. So it is secure under two computational assumptions. The hardness of decoding for large weight. I'm going to explain in a moment what I mean by large weight. And the pseudo-randomness of the code family we're using. So the decoding problem, I present it like that. So you take a finite field, FQ. Q will be equal to 3 for wave. The instance is going to be H. It's a matrix, a parity check matrix of some code. S is a vector of length n minus k. It's in fact a syndrome. And the solution of that problem is a vector of specified weight, t here, such that the syndrome of that vector is equal to S. In other words, there is a linear combination with t non-zero coordinate. You take t columns of the matrix H, and you add them with coefficients to obtain your target vector S. So this is a hard problem. It's NP-complete. It's well known. It's hard either when the target weight is small or when the target weight is high. In between, it's easy. By hard or easy, I mean here, easy is polynomial time, and hard is exponential time as far as we know. So the interesting part is that both ends of the weight profile provide hard problems. So I'll be interested, because I will talk about a signature scheme, I'll be interested in the multiple instance variant of the decoding problem, which is called DOOM, decoding one out of many. So you have the same kind of instance, except that in addition to the matrix, you have any number, well, a certain number of syndromes, and the solver is happy to produce the solution of a single of those multiple instances. So you have plenty of instances, you need to solve one of them. This is relevant for signature because it corresponds to the situation where the adversary produces a lot of favorable messages and tries to sign one of them. This is exactly what happens here. The interesting point here is that, well, the problem is easier, of course, when you multiply the instances, because you can always pick one of the syndrome and you get the original problem. So having more instances can only help you. I denote, and I will use dp infinity, the case where the adversary is free to choose any number of instances. It cannot be the infinity, of course, because at some point, just reading the instances will cost too much. So dp infinity is the easiest version of DOOM, and the problem, the DOOM problem cannot be easier than the decoding problem. In the sense, hard, easy, polynomial, exponential. So The doom problem will be easier in practice. The security exponent will be smaller, but you cannot go from an exponential problem to a polynomial problem. What are those generalized ternary UU plus V code? It's a very well-known construction in coding theory. It's used for Reed-Muller code, for instance. It's used for polar codes. And it has a lot of nice features. For those codes, the construction is used in a recursive way. So that it's kind of a fractal UU plus V construction where each block is again a UU plus V block. In this setting, we will build matrices with 4 blocks, which are arranged like that. So the top blocks will have the same matrix up to coefficients for multiplicative coefficient on the columns. Same thing for the 2 blocks that are down. But the matrices HU and HV are any matrices, so they are random matrices. So there's quite a lot of entropy in this family. You also have those coefficients by which you multiply the columns and a regularity condition, which I will not detail. Star is the Schur product. It's the component-wise product of 2 vectors. So you multiply component-wise the coordinates. I gave the definition according to the parity check matrix of the code. You have the same definitions with the generator matrix. And well, the point is that, the point I want to make here is that the dual of UU plus V code is also a UU plus V code. You just shuffle the coefficient and you take the dual codes of the component codes. Now, the nice feature of UU plus V code is that there is probabilistic decoding procedure that will allow you to decode a little bit more than a random code. So you can see the picture at the end, at the bottom of the slide. In the generic case, the easy region, well, in the bottom line, the easy region is slightly larger than in the generic case. So when you build an instance of wave, you are allowed to correct, to decode a little bit more errors than in the generic case. And this will be the trapdoor, and this is what we're going to use in order to build the signature scheme. Okay, so again, wave is an hash and sign signature. The public key is just a code, a ternary NK code. The secret key will be the trapdoor decoder I just presented. For a certain number W of errors, which is a parameter of the system. Of course, the public code will be a permuted generalized UU plus V code with well-chosen parameters. The signature is a solution of a decoding problem, and the instance which is solved is obtained by hashing. That's the hash and sign paradigm. So you hash the message, you obtain an instance of a decoding problem, and you solve it for W error using the trapdoor. The security of the scheme relies on 2 assumptions. First, the decoding problem in the multi-instance version is hard enough for the parameter. And second, the public code cannot easily be distinguished from a random code. That is, the public key will be a matrix. That matrix will look random in all respects. a little bit more. I'm not going to, that's not the point of the talk, but I need to introduce the gap here. So the framework on which we prove the security of wave, it's a GPV-like framework in which we have to prove that the trapdoor decoder produces signature according to a distribution which is independent of the secret. And this feature gives you an immunity to statistical attack, which is a nice feature for getting the proof. In our case, it requires an additional parameter, which is called the gap, G. It is used in the decoder, and it was introduced to reach a certain uniformity property that would be a bit too long to explain here, but the point is, the bottom line, the essence of what is the gap is the property that is at the bottom of the slide. The gap is a number such that a matrix M times M plus G as rank M. That is, it's a number of extra rows or extra columns you have to add to a square matrix to make sure that it is of full rank. Typically, so you want that to be true with a high probability, and exactly the exact value of G will depend on the threat model. If we go to the NIST threat model with the 2 to the 64 limit queries to the signature oracle, it means that you have to choose G of this order. 64 divided by log 2 of 3, that's about 40. Just to have an order of magnitude of what G is. Other parameters are more in the hundreds or thousands, so G is small. So how do you select parameters? First preview of how we are doing this. You choose N and K. For the NIST proposal, we always take K equal N over 2. Well, that's a choice. I will justify it. Well, I won't justify it, in fact. It's in the paper, but not in the talk. Then you choose KU, that's the dimension of the code U. KV is related to K and KU. So you choose KU and W such that this number W is the number of errors the trapdoor decoder can decode. So 2/3 of N plus KU minus G. That's where the gap is introduced. In fact, the gap is needed for the proof. A gap 0 is probably good enough, but we cannot obtain the uniformity proof, and we cannot really fit into the GPV framework with G equals 0. Well, so we have to lose a little bit of decoding power, so we do it. Of course, because that's how life is, we want W to be large against forgery attack, and we want KU to be small for key attacks. And as you can see, those two come in contradiction. So we need a trade-off between those two. And that's the point of what I'm explaining here, exactly how we reach that trade-off. Okay, forgery attack, it's something that is rather well known. There's a paper in SAC 2019 explaining what are the best techniques to solve the decoding problem for large weight in the ternary case, including for large weights. And so if you know a little bit about information set decoding and variants, it's a variant of information set decoding where the sub-USD problem is the generalized birthday algorithm, in fact, with an order quite high, like 4 or 5. Well, it's something that has been studied already, so we know about that. Key attacks is not as well known because this class of code is relatively new. The best approach that is known is to try to say something about unusual code word. I'm not very clear. I hope I will be clearer in a few slides. In fact, we are going to try to find type U or type V code words, whatever that means. So, forgery attack. This is a kind of curve we have. So this is for rate 1/2. So what I give here is the security exponent compared to the error rate. And I get a work factor that is of the form 2 to the c times n. And depending on where I am here, on the value of the error rate, I get a certain asymptotic exponent, and it gives me the block length that is required to, and the error rate that is required, that are required for reaching the security I need. So now about the key attack. So it's all about the weight distribution of generalized UU plus V code. So there are two subcodes, the type U subcode and the type V subcode, which consist of particular words that are formed only with word of U or only with words of V. So coming back to this definition, look at the generator matrix. It means that either the codes, the words that are produced only with the top rows, either the words that are produced with the bottom rows. And the point is that we know from Thomas Debris, PhD, and it also appeared in a few other papers, that except for those particular words, all the other words behave like random. That is, you won't get information from the other words. So if you want to get something about the weight distribution of UU plus V, generalized UU plus V code, you need to say something about those type U or type V. So they can be counted. We can know everything about those words. The important thing is this figure. I try to explain what it means. Again, it's an asymptotic exponent. So 1/n times log in base 2 of a cardinality. In black, we have what we expect for the number of code words in a ternary NK code. In blue, you have the number of type U code words for the same parameters. And in red, you have the number of type V. So first, we are going to discard the type V problem. This is typically what happens for all wave parameters. So type V code words never dominate. So whenever you're going to try to build attacks, there will not be based on type V code word. But if you look at those curves, you will see that on the right, there is a very small region, and on the left, there is a part where the blue curve is above the black curve. And that means that if you manage to find words of those weights, those words will be type U code words. And moreover, you will get those words much more easily than if the code was random. So if somehow the parameters are chosen such that you can solve the problem for the blue curves, for the type U code word, for one of those weights, then you have an attack, at least a distinguishing attack, and in fact, you can transform that in a key recovery attack rather easily. That's what I'm explaining here, and I'm not going to reread that. The important thing is that you can also make the attack on the dual code. So depending on the parameters, it might be easier on the dual code or on the code, because the dual code is also generalized UU plus V code, and if you know one of them, you know the other. Last thing is that the all cost for those search, so we are searching for code words using information set decoding algorithms. We are using the variant due to May, Maurer, Thomae, MMT from 2011. There are more elaborate variants, but at the moment, first they were not really generalized in ternary, but it's possible to describe them in the ternary case, but it doesn't seem to produce an improvement. So cannot be categorical about that, but the nearest neighbor techniques, the BGMM, the Baker-Joux-May-Maurer technique, might not improve a lot on that. So here is what I end with. I have my black curve, which is the forgery attack, and I have my other curve, which describes the same security exponent when I change the value of W, I change the composition of the UU plus V code, and I change the cost of the attack. So what I need to do, it's very simple. I will just pick the intersection of those two curves, and that's where the parameters are optimal. That's it, essentially. And here is the kind of parameters we are obtaining. You can read that in the paper, no problem. Important thing is that I'm speaking only of classical security, but the quantum security is always at least half of that. So we made this study. It's in the document we sent to NIST. We counted precisely the amount of quantum security, so we are safe with respect to the quantum decoding techniques. Okay, and now I'm ready to conclude. So in the end, we get a nice feature about the scalability. The block length, that is the signature length, scales linearly with the security, which is a nice feature. The key size scales quadratically with security, which is a bad feature. Well, that's code-based crypto, unfortunately. And the parameter selection process I just described can really easily be adapted to any evolution of the best-known attacks. I'm not saying that there will be an easy evolution, but I'm just saying that if ever someone improves this or that technique, we simply have to move a little bit those curves to find the intersection point and to get new parameters. And last, we are using code rate 1/2 for NIST because it's a good trade-off between key size and signature length. It's possible to tweak things a little bit. So if you want shorter signature, you can take higher rates. If you want smaller keys, you can take lower rates. But you don't gain much, and well, again, you can read details in the paper. Thank you very much.
All right, so what questions do we have? I'll let you stand there, please. I have a, oh, no, we can go first.
Your public key is in megabytes?
Yeah.
Is that right? What applications do you think this would be an appropriate tool for?
Typically, code verification.
Makes sense. Makes sense.
Wonderful. All right, any other questions?